Hello, this is Ian Schweitzer. A little video here in a series of videos that is going to help us solve a few problems here involving rates of chemical reactions. In the last video, we looked at a situation where we took concentration of items and looked at versus what we call initial rate. Okay, but we would like to be able to say, okay, if I were to do a chemical reaction and I want to track, okay, or again, predict the future, what's my concentration going to be down the road after my initial period's over? I could create a data table. I'm going to say A as a reactant versus time, T, okay? And let's just say A is a reactant, so it's going to start out relatively high concentration, and as I label out my data points, it would be essentially it would just drop off. Most chemical reactions would simply just the less A you have, the slower the reaction goes, and this thing just sort of nosedives. Okay. Now this is your typical chemical reaction. If you were to take the concentration of A divided by the time, concentration of A divided by time, you have a negative slope here. So the change in A over change in time would give you a negative value, and that would be your negative rate because you're losing it. Okay. For a zero order reaction, however, okay, it would look like this. A's concentration and time are not related. So rate equals K, and then concentration of A, and then 0. Okay, we would have a negative here just because we're losing a certain amount of A, but A, it would be lost at a very linear situation here because the concentration of A does not determine, this is 0 there, does not affect the rate. So I would just get this data from a data table, A concentration versus time. And as I have collect my data points, I'll get these data points, and I'd say, okay, well, in this case, it's just a straight line, it's linear, pretty easy to relate. Again, our overall goal is, after we get past this initial rate point, what's going to be the concentration later on down the road? This is quite easy. It's a linear relationship. I could use a proportion or a ratio, or I could use a y equals mx plus b equation, which is just an equation for a straight line. In this case, if I relate this equation, it's going to be the concentration, the y would be the concentration. I'm going to bump this up a little bit and put it right here. Okay, would be the concentration of A equals m, which is my slope. It's negative, so negative K. So this slope here, this is K. Right? Happens to be going down, so it just happens to be negative. X is going to be time, and then plus B, all right, which is going to be the y-intercept, which is just the concentration of A when it crosses this particular point here. Okay. Depends what it is. So there's 1, 2, 3, 4 variables. Algebraically speaking, give me 3 of them, I'll find the 4th. I will say, just for conversation point here, that because the slope here is the concentration divided by time, this equals the rate, which equals K. This only really works for zero order reactions. Keep that in mind. Okay. Now, this is following a PowerPoint, and the PowerPoint's located online, and it's pretty much just some mathematics. It's not real complicated mathematics, so I'll walk through the PowerPoint as I'm discussing a few things here. Okay. So we have just a simple rate reactions, just to review average rate versus instantaneous rate, mostly dealing with slope. A zero order reaction. Now, I will give you a worksheet, and actually the worksheet is actually on this PowerPoint, or I should say, not a worksheet, but a equation sheet showing some of these mathematical relationships. I have highlighted in red right here because that is the y equals mx plus b equation for a zero order reaction. The graph would be concentration versus time, y versus x. My slope is negative k. My units on k are concentration versus time. Now, unlike the instant rate law, okay, the units are less of an importance here. They are there, but they're less of importance as far as questions asked on AP exams. Okay, now let's go to a first order reaction. So I'm going to flip to my next page here for a first order. Now, for a zero order reaction, it works out nice because it's a linear relationship. So we can use a simple straight line reaction equation to find this thing out. But if I were to track the concentration of, let's say, A and time, then as soon as I started to, in lab, concentration of A, time, and start recording down some concentrations at various times, you'd see this sort of thing happen. All right? As soon as A degrades, we end up having a slope that just, the reaction slows down. So for this particular relationship, concentration versus time, A, it's going down, so we change in concentration, negative, we get a negative rate, meaning that we're slowing down. How do we know, this is an instantaneous rate here, but how do I know my rate at, let's say, time t? How do I know at this point? That is where our calculus equations come in. Okay. So what they've done is say, okay, let's find a different mathematical relationship that might be a little easier to track than concentration versus time. It turns out that, mathematically speaking, natural log of the concentration of A versus time ends up doing this. You take your same data from over here, okay, plug it in, and rather than doing concentration versus time, you do natural log of the concentration versus time. This mathematical algorithm takes our data, and it has to be a first order reaction. We'll learn more about what that means as far as a molecular level, but it takes our first order reaction, our bent line, and simply straightens it into a linear relationship. Now, from here, a lot easier to track for a straight line. In fact, any straight line can be, once again, listed as a y equals mx plus b equation. Y is going to be the natural log of the concentration equals m, which is my slope. Now, in this case, my units of my slope are the natural log of the concentration over time. So it's no longer the rate. So I'm going to cross that off. K no longer represents rate, but I'm going to call it K. And it's negative because it's going down. You should expect to have a negative rate. X is time, and then plus the y-intercept, which is going to be the natural log of concentration of A, right, at time 0. So they put a 0 to mean that that's where it crosses. Okay. Simple as that. This is a pretty standard algebraic situation. Give me 3 of them, I'll find 4. I'll find the 4th. Let's flip over to the PowerPoint and see what we do here. All right, flipping to first order. There is my equation. Negative kt, okay, plug it in. First order, there's my graph right here. There you go. Slope 1 over time technically would be my units. Again, not a lot of, in this situation, questions as far as on the AP exam about those units. But I will mention here, though, that when we have this initial rate right here, the rate equals K, concentration of A at time at first power, that this K right here and this K right here, they are the same. So if they want you to find the K value, and then you could take and substitute that K into here to find this, either way, this equation finds us the initial rate. Pretty simple. This one finds rate at different times. Okay, so either way, let's flip over to the next equation. Okay, that's second order. Let's do a that. Again, if I were tracking this thing, okay, concentration versus time, and I have my concentrations, I have time, and I'm tracking a second order reaction. Let's say I'm tracking A, and in that case, again, it would just start to dwindle off. A little bit different than a first order, but nonetheless, it would slow down. Okay. Mathematically, they say, okay, well, let's come up with a relationship that's going to help more easily represent these. And it turns out that 1 over the concentration versus time. And these relationships are purely mathematical. You could go online and find how they go from rate equals K, concentration of A, so power calculus-wise, into our new equation, which is going to be a y equals mx plus b equation, and you can find that derivation. For us, it just doesn't matter that much. Okay. Now, as you take this data and you plug it into here, it's going to be reciprocal, so it's kind of upside down, and you end up with something that looks more like this. Okay. The y equals mx plus b equation would be 1 over the concentration, which is at time t. Right. All of these are time t. My slope is k. It's just 1 over the concentration versus time. And of course, that does not equal the rate. It's just the slope of this line. X would be times the time. And then this is going to be 1 over the concentration at time 0. We're across the y-axis. A couple things I might note is that this happens to be positive because it's inverted. Again, simply 1, 2, 3, 4 variables, and you give me 3 of them, I'll find you the 4th. Okay. All right, flip to the PowerPoint. See what we got here. There's my equation. We've got a positive slope. Okay. Let's look at a couple different problems that we will see here to see how we might use these equations. This is the chart that I will give to you. And it just shows the equations. These y equals mx plus b equations are important. This is what we'll use to solve. As far as the AP exam goes, as of 2014, the introductory chart, which I know was not solidified, so what we get on the AP exam might be up in question, but the introductory chart will give you the natural log, the first order and the second order. The 0 order is not given on here. So they'll give you, so far as I can tell right now, they'll give you this one, they'll give you this one, and they've given you this one on the AP examination chart that I have in front of me, and that might change as of 2014. You can see the time on the bottom here right there. So either way, that will be yours to use. So what can we do with these things? Well, you could solve for different concentrations given time. For this, you need an order, and you need a K. So you need to know, is it 0 for a second? Give me a slope of my line, I can find it. Because all of our relationships end up being linear in the end as we mathematically convert them. Solve for a time in which a concentration will occur. Okay, so you need a time. Well, I can give you time. You give me the order, so which equation I got to use, and give me a slope. I will find you a time. Determine the rate constant. Okay. And we can also determine the order. These are some things we're going to do here. All right, so I'm going to go through here really quickly here. Determine the concentration at a given time. So here's the first question. Time required for half a substance to react is 726 seconds. Now, one thing that I'll mention here is what's called a half-life. Now, for half-life, let's flip to a new page here. Half-life is fairly common. Okay, and this is the time it takes for 1/2 of a substance to react. Now, I see this happen lots of times in areas involving radioactivity, radioactive substances, but you also see it in drugs. For example, the half-life, of caffeine, I spelt that wrong, but either way, is about 2.5 hours. It's just off the top of my head. It's about that. I don't know the exact amount. You can check that online if you want. But this is essentially how long it takes your body to rid your bloodstream of about half of the caffeine from you. So you know that, for example, if you have a nice little soda, okay, a little Coke, let's say at 7 o'clock, okay, 7 p.m., that means that if X represents the amount of caffeine you have in your body, and let's go by this number, then at 7, 8, 9, at 9:30, you would be down to 1/2 X in your bloodstream. And then at 9:30, 10:30, 11:30, midnight, okay, you'll be at 1/4 of your X value for your concentration of caffeine. At 2:30, okay, a.m. in the morning, you'll be at 1/8 X concentration of caffeine. So if you wanted to, at this point, you could hypothetically figure, okay, if I'm going to have caffeine, maybe I want to have it at before 5 so that when I want to go to bed, the concentration is dropped off at this amount. Okay. Now, for this value, let's see what our question says. It says it takes 726 seconds, starting with concentration at 0.6. What will be the concentration at 1452 seconds? Okay, it's first order. Now, if you look at this mathematics here, they're giving you 1452 seconds. So at this point, how many half-lives is that? 1452 divided by 726 equals 2. So at this point, I would say, okay, this 0.6 would drop from 0.6 down to 0.3 at 726, okay? And then at another 726 seconds, it would drop from 0.3 down to 0.15. That's just off the top of my head using half-lives, okay? Again, at 726 seconds, the 0.6, I think that's what it was, drops down to 0.3. Another 726 seconds, it drops from 0.3 down to 0.15, half of that. So that's your just standard. So it's going to take, room here. All right. So what is the half? So what is its first order? What is the half-life? Well, it's 726 seconds. Can you solve this problem with only half-lives? Okay. Let's look at the math on this here. So it says times 0, 726, and there it is, so 0.15. Use the equation to determine K. It's first order. So what is my K for this chemical reaction? Because it's first order, I can use this equation. You can rearrange if you want. I just move this over here, get this on one side because I want to find K, and then I get natural log of the concentration times T divided by the natural log of, the concentration of O. So we're looking at some rules involving natural logs. When I kick it over, I subtract this guy. Subtraction of natural logs is the same thing as dividing. Now, for a first order, okay, now this is important. I'm going to rewrite this thing on this other page here. All right, so it is going to be the natural log, okay, of essentially one. Let's see what we got here. The natural log of 1/2, and if you go 0.5, the natural log, okay, so it's going to be, in this case, natural log of 1/2, okay, equals, okay, I just subtracted that thing off this other side, so I took this guy, subtracted it off, leaves negative KT behind. That's important. So equals negative KT. Take your natural log of 1/2. Now again, it's a half. So if we go from 0.6 down to 0.3, is the same thing as going from 2 to 1. My fraction still is a half. Okay. So at this point, the natural log of any half-life for a first order reaction only, all right, is negative 0.693. Equals negative KT. All right, so if I want to find, then at this point, because I've done the 1/2, I always put a 1/2 here. time for 1/2, and divide out, and we get 0.693 divided by my t 1/2 equals my k, or 0.693 divided by my k equals my time for 1/2. This particular equation right here is actually also on the introductory advanced placement equations constant sheet for as of this date. Now, first order reactions, just telling you, are the most common. This mathematics here, everything I've talked about so far, only works this well with first order. If you start looking at your second order reactions, not going to work out so sweet. We can look about why that is on a molecular view on a future video, but at this point, simply is not going to work. First order reaction generally is something where you have one item and it's breaking down. Okay? A second order reaction would have to have two items coming together, and that it gets more complicated. So the majority of our problems that we'll have involving half-lives will involve just first order reactions. Flipping over, solving this problem, and how long will it take the previous experiment to reach 0.1? Alright, so here's our mathematics. This is the same equation, keep in mind for first order, just subtracted it over. You plug in your values, and the time is equals 1880 seconds. Graphing, using graphing to determine an order reaction. This is like the last new item that I want to just throw upon you, and then we'll be pretty much done with this video. All equations are y equals mx plus b. If data correctly matches up with that equation, the line will be straight. Therefore, a reaction will only match up with one of the equations. The matched equation is the order. So, if we take some data, and we have just again a plot of x, y data, and I know that if it's 0, okay, here's my 0 equation, concentration versus time. If in fact that the concentration does not have any effect on time, this should be a straight line, and it's not. Plot it out on my natural log versus time. This is the first order, and it ends up being straight. Okay, nice. My second order is not straight as well. So in this case, the straight graph will indicate the order of the reaction. Given a plot of data, okay, and again, this is the last cog to being able to figure things out here of this thing. Graph to determine order. All right. We have, someone just throws data at you. All right. X data, time, all this stuff here. How do you figure out the order? Okay. You do 3 graphs, and a lot of times they'll never have you do this on an AP exam. Okay. But they might give you these graphs and say interpret them. Okay? This one would be concentration versus time, natural log of the concentration versus time, and 1 over the concentration versus time. I've even seen them say, okay, here's some data, explain how you do it. You don't actually have to do it, just explain. I would graph all 3, indicate how you would graph them, and the one that gave you the straight line would be the order. So this one might look like this one might look like this as well, and all of a sudden this one ends up being straight as an arrow. Therefore, this reaction is second order. Okay. Other than that, I think we're pretty much done here. You can take a look at this PowerPoint and do, well, that's pretty much the end of the PowerPoint. So we'll stop there. Thank you.